Bismillahirrahmanirrahim. In this video, I'll try to explain what is capability curve of a synchronous generator. And to augment our discussion, I'll also solve part A of example 5.8. So, as we know, the synchronous generator has a body. This is called the stator, on which we have armature winding, and this is rotor, on which we have field winding. Now, our aim should be to protect both of these windings from overheating, and that determines the limitation or the capability of this generator. And generally the parameters are given on the panel diagram. You can see power factor is given, speed is given, this is the terminal voltage Vt, the capacity in kVA, this is the apparent power. Then we have rating in kW, this is the real power, frequency, current, this is armature current, and field current. So these are given. And at the end of the lecture, we'll be drawing a diagram something like this. So this is will be called the capability curve. Okay, we have learned this, that the per phase equivalent diagram of a synchronous generator is represented like this. We also know how to write the equations. EA is dropped in this branch, and its a phasor diagram represented like here. I'll not discuss because I have discussed all this in the phasor diagram video for later. Now, a simplified version is when we ignore RA, where RA being very small than XS. Then the simplified diagram will be this, or this circuit will be this. Equation will also be simplified, and the phasor diagram will also be simplified. This term is eliminated from here. So we'll work with this phasor diagram. Now, if we resolve this portion, only this portion, if we resolve, then we'll have two components, the vertical component and the horizontal component. And if we just tilt little bit like this 90 degrees, only this part, then it is visible that this is angle theta, and the opposite arm or the perpendicular is the sinusoidal terms, and the base is the cosine terms. Now in this case, this angle is here, so this will be the base and this will be the perpendicular. So this is XSIA cos theta, and this is XSIA sin theta. Now you might ask where from we are getting this theta. So for that, I have a diagram here which you can follow. We have drawn a parallel line this to IA, therefore this angle is theta. And this line is 90 degree from here, so it will also be 90 degree on this line. So this is 90 degree. If you subtract theta, then this part is 90 minus theta. And if you draw a vertical line, then this is also 90. So this is 90, this is 90 minus theta, therefore this has to be theta. Okay, so we are here. And now we want to convert this. This is in terms of voltage, everything, voltage diagram. We want to convert this diagram into power diagram because our losses, etc., are in terms of a real power or reactive power. So we want to convert this into power diagram, and this is the formula, one of the formula for power. This is the real power, 3V phi Ia cosine theta. And now if you compare these two, what we have to do to convert this into this. So look here, if you multiply this term by 3V phi over XS, then we get this result here. So that means this is the multiplying term. So we'll use this term to multiply all the parameters to convert this diagram into power diagram. And so multiplying this, this, everything by 3V phasor V phi over XS. So this is our power diagram. We'll now write it neatly, multiplying. We get this diagram here. You can. Now this is the real power. V3 V5 Ia cos theta. This is real power. We know the cosine terms is with the real power, and the sine term is with the reactive power. So this is reactive power, and the summation of the two will give us apparent power. We know this formula. S is P square Q square under root, and if you use these two, square them under root, then we'll get this value. Therefore, this is our apparent power. So we write apparent power. So this is complete power unit diagram. Now, there's one thing that we can notice from here, that the origin is at this point. So origin is here. This is our vertical line. This is the horizontal line. Now this point here is actually, this distance is 3v5 square xs. So we can say that this origin is at 3v5 square over xs. Now we want to bring the origin here. So what we have to do, if you subtract from both 3v square xs, then this will become 0, and this will become minus 3v5 square over xs. And now if we implement our this apparent power on this diagram, so our diagram will look like this with the apparent power. So we were here. Now I want to note that we know that the apparent power, the reactive power could be positive or negative, whereas the real power will be positive. Now to show that, we'll just tilt this diagram a little bit, turn it. Okay, the lines of constant armature current Ia as lines of constant S is 3v5 Ia, which are concentric circles around the origin. So let's see what it is saying. What we have done is we have tilted this here 90 degree, and now you can see this is negative, this is positive. So reactive power now we can represent by the vertical axis, but this is on the negative side. We want to turn it further, so flip it horizontally. Then this is a more convenient diagram. Now our power is the positive, or the wattage power is in the positive direction, and reactive power is positive, negative both. Now this is our apparent power. So that is what is saying, that the line of constant armature current Ia, if the armature current is constant and phase angle changes, then what we'll have, will kind of get a circle here. So that is the concentric circle around the origin. So it will be something like this. This circle will represent the power consumed by the stator winding or the armature winding. So this is our apparent power from the diagram. So this is armature winding or stator winding power consumption, or the limit, we can say. Then we come to the field current. The field current is proportional to the flux, and the flux is proportional to EA by this formula. Therefore, this diagram, which was representing EA in the voltage diagram, and now in the power diagram it is 3EA V5 over Xs. So this diagram, or this arm, will represent the field current. So here also we'll tilt it to bring the reactive element vertically, and after tilting this we further tilt. So this is more plausible diagram now. And now this is our origin from here, and this is the end point. This is the end point, and this will be representing the field current, and so we can represent it by a circle. So this circle, you can see origin, this radius, and we have drawn a circle. So this circle will represent the field winding or the rotor winding limit. The line of constant field current corresponds to the line of constant EA, which are shown as the circle of magnitude this. So this circle is of magnitude here, and its origin is at minus 3V square XS. So what we have got two circles. One is for the armature current and the other is for the field current. And now we can combine them, keeping this origin same at both places. So the combined circle will now look like this. And now we can from here extract the exact limit. And what will that be? Now look from here. This is the lower of the two, so we'll accept the lower one, reject the upper one, so we'll get this part. Then, as we mentioned, that our power, real power cannot be negative, so we can eliminate this part. That is eliminated. So this is what we are left with. Now, one more thing, and that is shown here, is the maximum prime mover power. Now, the prime mover have its limitations, like the turbine or any other thing which is moving the generator armature. So that has its limit, and in the next question that we'll solve, we'll see that this point is 50 kilowatt, but the armature, the prime mover limit is 45. So that means it is also imposing a limit. So we draw a line here, and so this part is now out. So our diagram will be now like this. This is our limitation diagram or capability diagram for synchronous generator. And someone, Mr. Ferdinand Gordon, has drawn it very neatly, so I just courtesy, I'm reproducing it here. You can see this was the field current limitation. This was the diagram for the armature current, and this we have selected, and this line was for the prime mover. So this red is the our area of the capability curve. Okay, so with this background, now let's solve a question to further augment our knowledge. This is the question given in the book, and it has 4 parts. I'll not do part B, C, and D. I just want to explain what is the capability curve from the diagram. Okay, so the first of all, we'll plot something like this. So let's first of all see the center of EA circle. Now this was the center, negative 3b5 square over xs. So xs is given here, reactance is given. We don't know v5, but we know the terminal voltage, and for Y connection generator, the relation between the terminal voltage and the line voltage, terminal voltage and phase voltage, this is terminal voltage, is V terminal or VL divided by under root 3. So our V5 will be 277 volt. And therefore the center of the circle, putting value of now V here, X. So the center of the circle will be negative 230 kilovolt ampere reactive. So we write it here. This is our origin. And now we have to find this magnitude to draw this circle. 3EAV5 axis, that is the magnitude or the distance, which we are calling it DE. We have found this, we have found the center. Now we need to find DE. So DE is given by this formula. So this is dependent on the EA, or this is proportional to the EA. Now, how do we find EA? We have already learned from this graph that this is the formula for EA, that is EA is a vector sum of V phi and JXA. So this is the from the voltage diagram. We know V5, we know XS, but we don't know IA. So IA we can find from the power. We know this is the power formula, apparent power formula. S is V5 IA. S is 50 kilovolt ampere. So we'll use that to find IA. And in the book he has written the rated current and rated voltage, etc. But the formula remains same. So 50 kVA divided by 3 divided by V5. The armature current is now 60 ampere. So this is the magnitude of the current. So magnitude we have found 60, but we need to find the phase angle. Now the phase angle we can find from power factor lagging. So we know that the theta will be cos inverse of the power factor, and this will be minus 36.87, minus because of lagging. So now we put in the values in this formula. Formula 277, angle 0, it's a 1.0, current 60, current's angle, and by using your calculator in complex mode, you can solve it in one step. So EA we have found, and now we'll put the magnitudes of everything here to find the distance DE. So DE is EA 317 from here, B5 277, so 263 kilovolt ampere reactive is the distance. Okay, now we take a frame for this graph, and we have gone up to like minus 250. Our Q is minus 230 kVR. So we find a point here, minus 230. So this is the origin point. And then we have also found DE 263. So from here, we're taking a 263 kVR radius, we draw a circle. So the circle will be something like this, 263 kVR radius. And now from this diagram, this was the P power, PV5IA. So we can find the power to be 49.86. That means the circle that we'll draw will be of this power. This circle from here will be of 49.86 kilowatt per kVR. With this radius, we draw a circle at the origin. And now, as we had done in the theoretical part, we'll eliminate the upper portion of this, we'll eliminate the left side, and if there is a prime mover limit, we'll incorporate that. So let's incorporate the prime mover limit first of all. We have got this. Prime mover is capable of supplying 45 kilowatt. This is given in the question. So we have to draw a barrier here at 45 kilowatt line. So we drew this line. So now our limit is this is out. Upper portion is out. This whole left side is out. So this will be, this is the graph drawn in the book. But I think a more appropriate will be something like this with the red color that I have done. So this is the real capability curve. So I hope you have been able to follow. I got some idea to what is the capability curve, why we need. This gives you an idea about the operating limit synchronous generator. Thank you.